Okay, guys, let's go ahead and look at Module 4. This is Module 4 Protocols. Remember, I won't be going into great detail, but I will hit the high points and kind of give you an idea what's going to be on the quiz. So make sure you absolutely go back and read the chapter and look through these notes yourself, but I will try to kind of hit the high points. So let's go ahead and see what we have here. That was scary. All right, so here we are in Module 4. The objectives, as always, by the end of the module, you should be able to describe the function of the core TCP IP protocols, and there are several. Identify how each protocol's information is formatted in a TCP IP message. That's going to be where the things are in the packet, where the header holds its information, and what the little pieces of the header mean. Also about securing network connection using encryption protocols. That would be TLS version 1.2 and 1.3 as of this recording. Those are the current ones. And so we're going to kind of look at how that happens and particularly in what layer it happens. Also configuring remote access connection between devices. As you've seen already in the labs, we can use remote desktop. We can use web-based applications like TeamViewer. There's several different ways we can connect remotely. And then finally, employ various TCP/IP utilities, particularly command line utilities for network discovery and troubleshooting. So we'll look at the ARC table and just different pieces that we can use in our daily task to get the network up and running or to keep it running. All right, so let's get on with it here. Okay, as you should be aware, TCP/IP is not just one protocol. It's a suite of protocols, including TCP and IP, version 4 and version 6, UDP, ARP. There's several others. We'll talk about those later, but these are the main ones that we're concerned with. TCP/IP protocols add a header to the data inherited from the layer above it. Okay, so layer 7, 6, and 5, data and instructions. This is the payload. This is what's generated by applications like your browser or your email client, whatever's programs you got running on your computer. And then layer 4, this is the transport layer. This is where either TCP or UDP, depending on what you're using, adds a header and basically puts together or encodes, not encrypts now, but encodes the data. And this is where the port number is applied. So when the application on the other end of this message, the receiving application, this port number will tell it what program to use to react to or to digest this data. And then layer 3, the network protocol, the IP layer, this is where it changes the data into a packet. It adds another header on top of the header that TCP added, and now things coming out of layer 3 are called a packet. They go on down to layer 2. This is the data link layer on the network card. This encapsulates the packet inside of its own header and trailer, and here at layer 2 we call it a frame. So we have packets inside of frames. And then finally layer 1, this is where the actual network card sends the data out onto copper wire or out to fiber optics or out to the internet anyway. So this is the physical layer. This is where the actual transfer of data takes place. Let you go ahead and go through these. This is basically just the forward and backwards of data going through the different layers. So it starts off layer 7, the application sends it into your computer, presentation layer, sessions, transport, all the way down. Then it goes across the internet and it is received at the number 1 layer. That's the physical layer of the receiver of that communication. And the receiver sends it up through the OSI layer. So the physical layer sends it to the data link layer, which strips away some of the information that the sender had packed around it. It goes up to the network layer, and that's where some more headers and trailers are stripped away, all the way back up to the receiver's application layer, where it goes to whatever program based on the port number that the data is addressed to, and then that gets reacted with, or something happens and it may or may not send a message back. Receiving host decapsulates the message in reverse order, just like we went through, and presents the payload to the receiving applications in layer 7 of the receiver. Connectivity devices are specialized devices that allow two or more networks or multiple parts of one network to connect and exchange data. TCP operates in the transport layer, and that's a thing you will need to know. TCP operates in the transport layer. There are three characteristics of TCP. It's connection-oriented. There's a three-step handshake process that allows us to build TCP connections. It does error checking. It uses checksums and sequences to make sure that all the packets are there that make up a message. And it can have flow control, which controls how much information is going to the receiver, and it's based on how quickly the receiver can accept the data. Okay, and this is what a TCP segment looks like. The source port, that's where it came from, the port number, and then the destination port, that's the one it's going to. Sequence number means what sequence in the list of packets. Acknowledgement, that's part of the connection process. Header length, and then all the different pieces here. Sliding window size, checksums, urgent pointer, options, and then finally, after all this header information, then we get to the data. So this is what a TCP segment would look like. The three-way handshake, there are three messages that have to be sent back and forth. So the initiator sends a SYN message, SYN. The response to that from the recipient is a SYN ACK that says, yes, I'm here. And then the sender, the original sender, sends an acknowledgement of that. So it's three steps in the acknowledgement process, the handshake process: SYN, ACK, and ACK. After the three initial messages, then the payload or the data can be sent. If you're requesting a web page or an email or what, it doesn't matter. That information will be sent after the connection is made. Sequence numbers basically are increased by the number of bits included in each received segment, and that's how TCP can make sure that everything is there, because it has a total number that it gets, but it also has it keeps account of the numbers as they come in, and then when the total number equals the amount that it's expecting, then it knows that the correct length of the message was sent. Okay, so this is the connection process, a three-way handshake. So the initiator sends a SYN, that's the flag that is in the header, and then you can see the sequence, and of course the acknowledgement would be 0 because we haven't had one yet. And then the recipient, usually a server, sends back an acknowledgement in the SYN of its own, and then the original sender sends a sequence number and acknowledgement, and then it sends a final acknowledgement. And now that the connection is established, then data can be sent. UDP is similar to TCP except for some important considerations. Number one, there's no three-way handshake. It's basically just I'm sending you data. It does not guarantee the delivery of data. It does not do error checking. Basically, it's a quick spurt of data, and if it gets there, great. If it doesn't, UDP doesn't care. There's no error checking, there's no sequencing, there's no flow control. It can drown you in data. It doesn't care about the sequence, whether or not the packets arrive in the right order. It's more efficient than TCP, but not as reliable, which is why we use it for different things than we use TCP for. Video and audio, it's okay to send those like a live stream, because it doesn't really hurt if you drop a packet here or there. It doesn't really hurt the whole overall message. On the other hand, if you're sending a data file, like a text file or a picture file, it really matters that all the data gets there, because you don't want a big blank in the middle of your JPEG file. So it's also more efficient for carrying messages that fit within one data packet. A UDP header has only 4 fields: source, destination, length, and checksum. And the checksum is optional, but required in IPv6. So that's Actually useful information there. IP operates as the network layer, which makes sense because it's the internet protocol. It's the network protocol, and it operates in the network layer of OSI. It specifies where the data should be delivered, IP addresses. That only makes sense. It identifies the data source and destination IP addresses. It enables TCP to internetwork because it's the train that carries the content that TCP sets up. So to traverse more than one LAN segment or more than one type of network through a router. It's not reliable. It is connectionless. It does not do any kind of data checking or error checking. There's no session established. Basically, it's just a carrier signal. It carries stuff. It goes from one IP address to another. It depends on TCP to ensure the messages are put back together and in the right order because that's what TCP does. Okay, so an IP header would look like this. This is what a packet would look like. Version IHL diffs, I'm going to let you go through all these. But basically the things that we really need to know about are the source IP, the destination IP, the flags, whether it's ACK or SYN, things like that, protocols, whether it's TCP or UDP, and then finally we get down here to the TCP segment, and then inside that we have the data. So see, each of these headers is stacked on to other headers. IPv6 uses a different packet format, a much bigger format. There's a lot more information in the IPv6 packet. There's no fragment offset fields, and the IPv6 host adjusts packet sizes to fit the requirements before sending the message. ICMP is a core network protocol. Now this is another member of the TCP/IP protocol package. It's a core network protocol that reports on the success or failure of data delivery. You need to know. It can indicate the following: when part of a network is congested, when the data fails to reach its destination, and when the data has been discarded because the allotted time allowed here has expired. It announces transmission failures, but it cannot correct errors. It can find the errors, but it can't detect or it can't fix them. It provides critical information for troubleshooting problems, though. If you are a network technician, you will use ICMP applications to determine what's going on with the network. And on IPv6 networks, it performs the function of ICMP as well as ARP. The same thing that an ARP table does on IPv4, ICMP version 6 does on IPv6 networks. ARP works in conjunction with IPv4 to discover the MAC addresses of a host or node. That means it goes out and gets the information about the MAC address from the network cards of the hosts that are on the network. It builds a table, it builds a local database. It's a layer 2 protocol. It uses IP, and layer 3 relies on broadcasting. Operates only on local networks, so there's not an internet ARP table out there. It's basically a database of IP to MAC addresses, which you have a MAC address or a physical address on your network card. Your computer has an IP address, and this ARP table connects those similar to what a DNS table does with URLs and IP addresses. 2 types of entry, imagine that, static and dynamic, just like DNS. And to view a Windows workstation's ARP table, the command is ARP-A as a parameter at the end. So ARP space -A, and that will give you the ARP table. And it looks like that. And basically what it has is all the different interfaces, the different connections on the network, and whether they're static or dynamic. So this internet address, 192.168.56.225, would be tied to this physical or MAC address, this FFFFFF, which MAC addresses are all hexadecimal numbers. So if you look at the picture, what you're seeing is a connection between internet addresses and physical addresses. This internet address, let's say down here, is associated with this network card, and this is associated with this network card, and so on. Neighbor discovery protocol is an IPv6 thing because two adjacent nodes, or two nodes that share the same network, are called neighbors. And so NDP, the neighbor discovery protocol, carries ICMPv6 messages automatically, and it detects neighboring devices. And remember, we said that ICMP version 6 does the same job basically as ARP and IPv4. Well, this is part of what it does. It goes out and detects neighboring devices, and it determines their MAC addresses and also their IP, among other things. Ethernet. And this is the most important data link layer standard because all networks to some extent run on Ethernet, or Ethernet 2's current standard. But essentially this is the network layer. It's how modern LANs are connected. It's how the nodes on a LAN or a WAN or PAN or whatever you want to call it, it's how they're connected. This is where the frames are built. And basically this is what a frame looks like. And then inside the data area, that's where the packets are from the IP layer. Protocol headers include the source of the MAC address, and that's going to be Ethernet. It encapsulates the data with a header and a trailer, creating a frame, and the stuff inside the frame is the packets from the IP layer, and the frame includes the MAC address of the sender. Encryption protocols, basically TLS, and now we're up TLS version 1.2 and 1.3 are usually what you'll see. SSL, you may have heard, secure socket layer. Really not, that's actually a really old security protocol that's not used that much anymore. Now it's all TLS. SSH, pardon me, that was actually a thing invented way back in the Netscape Navigator days, but Microsoft has replaced that with their own flavor of security, and basically it's TLS. So version 1.2 and 1.3 are what are currently being used. Encryption, the general idea behind that is to keep information private. Now, there is a standard for data security, and if you know anything about cybersecurity, or if you're interested in that at all, one of the very first things you learn about is the CIA triad. This has nothing to do with the intelligence agency. This is not the Central Intelligence Agency. This stands for confidentiality, integrity, and availability. Confidentiality means we keep the information private. Unauthorized viewers don't get to read it. Integrity means we keep the same information. We don't allow the information to be changed during storage or transmission. And then finally, availability. The people that need it need to be able to get to it. And so you can't, you can make the network so confidential that availability is non-existent. I mean, if you lock the data up, no one can read it. You don't have to worry about it being stolen or changed, but availability. So these are interrelated like that. There's an inverse proportion. So as confidentiality goes up, availability usually goes down, and so on. So, but remember, the CIA triad is not the government intelligence agency. Basically, it's just confidentiality, integrity, and availability. A key, we encrypt data based on keys, and we have to be able to get that key to our receiver of our data so that they can use it to decrypt. We'll look at that process a little more in detail in a separate lecture, but basically you've got a private key and a public key, and you use the public key to send that out, and then the receiver can use the public key to generate a private key. Once they have the private key, then they can decrypt the data that you send. So what we got, the sender encrypts with the private key. This is called private key encryption, and the receiver decrypts with a private key. And that's just private key. Now the problem with private key encryption is at some point you've got to get the key to your receiver, and you can't send it out over the internet, because the minute a private key goes out over the internet, it becomes suspect. That is a very common security thing, that if the private key ever goes out in its final form over the internet, it's no longer trustworthy. So private key encryption involves you figuring out some way to get the private key from your computer over to the receiver's computer. Now that can be, you have a guy with a briefcase chained to his arm, and he has a flash drive inside the briefcase. That's possible, depending on how much you trust the guy, but you can't send a private key out. So private key encryption means there's only one key, the private key, and the sender uses it to encrypt, and the receiver uses it to decrypt. The trick is getting it from the sender to the receiver securely. Public key encryption, on the other hand. So the sender has a private key that he encrypts with, but he also has a public key from a keying authority. He has a certificate, basically, and that's with that public key, he gets a copy of it from a certificate authority. The receiver gets a copy of that same public key from the receiving authority, and then the receiver uses that public key in a mathematical process. There's an algorithm of some kind, and that generates the same private key that the sender has. So you never have actually sent the private key over the internet. This is how public key encryption works. So both of you have a copy of the public key. You're able to send that public key to the receiver. But it's not the private key. There are pieces of it missing. The receiver has not only a copy of the public key, but he has the ability to use that public key to generate a private key. And now once he has the private key, you and the sender and the receiver can communicate securely, because the private key that the receiver generates will decrypt the information that the sender sends. Hope that wasn't too confusing. IPsec is an encryption protocol. Basically, it allows for the encryption, authentication, and key management for TCP/IP transmissions. There are 5 steps to a secure transmission. That's IPsec initiation, key management, security negotiations, data transfer, and termination. Those are the 5 steps in a secure connection. 2 modes it operates in: transport mode and tunnel mode. I'll let you guys get the definitions. SSL and TLS. As I said a while ago, SSL is not really in use anymore. The actual SSL protocol is old, and it's not reliable. TLS, on the other hand, is the current method, and the version for TLS is version 1.2, 1.3. These are methods for encrypting TCP/IP transmissions. Protocol, or when a client and server are established that kind of connection, they establish a unique session, which is an association between the two. It's defined as an agreement on a set of specific encryption techniques, and the session is created by what we call an SSL handshake. The handshake protocol allows a client and server to authenticate. It's similar to what happens with a TCP three-way handshake. Remote access that allows a client to connect or log into a server, LAN, or WAN from a different geographical location. There are a lot of ways to do it, but they all require some kind of a remote access server, whether it's a web-based application that allows you to remote in through TeamViewer or something similar to that, or whether it's remote access via remote access desktop, which is built into Windows. You still have to have a server and a client. Two types: dedicated devices. That would be an actual hardware piece or software running on a server, and that would be like remote access desktop, something like that. Types of include remote file access, which basically allows you to store and retrieve files as though you were inside the network, inside the LAN, through the use of a VPN of some kind. Terminal emulation means you're logging in like remote desktop, like we did on the last lab. Basically, you're just logging in and you're running a mouse and keyboard that affect the remote computer just like it would your own computer. FTP is basically a really old protocol for file transfer. Now everything has to be secure. FTPS adds a layer of security and encryption to it. SFTP is another secured flavor of FTP that includes encryption and authentication. And then finally, trivial FTP. There's no authentication or security. This is what old regular FTP was like. Nobody uses this anymore if they have any good sense at all, because basically it's just out in the open and it's very simple to intercept this kind of a transfer. In fact, it's one of the ports that hackers look for when they're port scanning a computer. If you leave port 21 open, you're putting yourself into a serious situation. Terminal emulators like remote desktop. It allows a user on one computer to control another computer through a mouse and keyboard. Telnet and SSH are command line softwares. We've used SSH. We would have used Telnet, but nobody uses Telnet anymore. It is also basically just wide open. If you have Telnet enabled on a server, you can bet that your server has already been hacked. But SSH is the ability to log into a command line like we did, and then you can run whatever command line commands you need to run, do whatever file operations you need to do. GUI-based software like TeamViewer, VNC, Remote Desktop, those are all terminal emulators. They allow you to log in and run the computer remotely using a mouse and keyboard. Telnet, like I said, this was big back in the day, but nobody uses it anymore because it has no security whatsoever. SSH, Secure Socket or Secure Shell, allows you to log in like Telnet to a command line, but it also allows for authentication and encryption, and it protects you against a number of security threats. It allows password authentication using public and private key generation, so it's very secure. This is PuTTY, which we don't use anymore here, so unfortunately we're not able to download this. They have putty.org blocked. This is actually a good terminal emulator program, or not terminal emulator, but a good SSH program, because it allows you to log in and allows you to store connections. It allows you to add a lot of different modifications in, particularly if you prefer to use GUI, graphical user interface with mouse and keyboard versus command line. Some people just don't like command line, so this is a good alternative. But for us, for our purposes, we're going to use command line because, frankly, it's already built into Windows and there's no need to download an external program, which IIT doesn't really like us downloading anyway. RDP, Remote Desktop Protocol, is what Microsoft uses with the Remote Desktop application. VNC, Virtual Network Computing, is a cross-platform RFB. Basically, it allows the same kind of thing to remotely control a workstation. It's open source, so other companies build on the VNC platform, and they make their own little flavor of it. Out-of-band management relies on a dedicated connection between the network administrator's computer and each network device. I'll let you go more into detail on that. VPNs, basically it It allows for an encrypted end-to-end connection, basically a tunnel, and it creates a private connection to a remote network. This allows you to act as though you are on the LAN. You have access to network applications and network file sharing, just like you were in your office, but you're actually at home. You can have site to site, client to site, and then host to host. And I'll let you go through and find the definitions of those. Special VPN protocols are encapsulated in higher layer protocols in a process known as tunneling. We talked about that. It's a secure end-to-end data tunnel, basically. It allows you to act as though you're on the network, but you're not really. These are the four different protocols for the connection. Layer 2 tunneling, generic routing, OpenVPN, and IKEv2. This is what a VPN frame looks like. Basically, it takes the original packet from the IP layer and puts more header and trailer information on it until finally it is able to transfer in the VPN stream. We're not going to talk a whole lot about Cisco. MGRE, multipoint GRE, allows the configuration of multiple tunnel destinations to a single interface. Cisco is kind of its own thing. I encourage you highly, learn everything you can about Cisco interface and about how to set up a Cisco routers, but I will tell you it is beyond the scope of this class because it's a fairly involved process. Cisco is a specialization all its own, but it's definitely worth having because Cisco's probably the most popular router technology in the world, so it's definitely worth looking at. Policies for remote access, these are be based on your company, but these are 8 or 10 of the more common things that everybody should consider. Remote devices should be up to date with patches and antivirus and whatever. Device access got to be controlled by a strong password. Biometric, there's too much opportunity for spoofing there. Password should be strong and must be changed periodically. That's normal. Device's internal and external storage must be encrypted. Also normal. Company and customer data must be kept secure. That is very, very important. But basically, these things are just stuff that's common sense. Troubleshooting. The applications we're going to look at are NetStat. Displays all the TCP connections that you may currently have. If you run NetStat, it will show you every connection that you have on your computer. Usually they're web-based or connections to a printer if that's using TCP. If you have a remote printer or network printer, any internal connections you have from loopback addresses, all of those things will come up using NetStat. And then traceroute, we've already used that several times. Basically, it measures or it delineates the hops between the source of the message and the destination of the message. So if you trace route to yahoo.com, it'll go through all the servers between your computer and yahoo.com. TCP dump, it's a packet sniffer. Do not run it on a network that you want to remain friends with the people that run. It captures traffic that crosses a computer's network interface. It does that similar to what Wireshark does. It's a packet sniffer. So it keeps up with packets, and you can also do some other things that network administrators really don't like other people to do on their networks. The output can be saved to a file, so basically you're saving it like it's like a Wireshark file. You're looking at those packets, and then you can filter them, and you can go back and analyze them. It is a Linux-based thing, and you do have to use sudo to be able to use it, or you have to be logged in as the root administrator. Otherwise, you cannot access that application. Duplicate MAC addresses, spoofing is a problem. Generally, what will happen is if operating system detects a duplicate MAC address, just like it detects a duplicate IP address, it will start sending you messages about what devices have duplicate addresses, and then allow the network administrator to handle it on their own. Hardware failure, you would use traceroute to track down which NIC is failing. What you do is you send a traceroute past the device that you suspect is failing, and it will generally, the traceroute, which you've seen before, the traceroute will fail at the device and it won't go any further. So that gives you a really good idea where the failure is at. Protocol must be followed through a firewall for traceroute to connect, and that would be ICMP, because that ping protocol, which is what ICMP is the thing that it's the protocol that traceroute uses to contact all the nodes between you and your target node. All right, so this is the goals for this module. Describe the functions of the core TCP/IP protocols, identify how each protocol's information is formatted in a TCP message, secure network connections using encryption protocols, configure remote access connections, and then finally employ various devices or applications like traceroute and netstat, things like that, for network discovery and troubleshooting. All right, guys, so that is Module 4, and once again, you really need to go through and read the material in the chapter. Don't depend on me, because this is just a really high-level overview. So if you want to get the information, you need to read the chapter. Make sure you're staying caught up with quizzes, lab on Monday night or Thursday night, depending on which section this is, depending on what section you're in. Could be Monday, could be Thursday night, but don't miss out on lab. Make sure that you stay caught up, and if you have any questions, I can be reached through the Canvas inbox, or you can ask me during class. In the meantime, have a good day.